given a switched network, a set of switches, what's the best path through that network to get from one source to one destination? And we gave some informal introduction last week, giving some examples if we want to drive into Bangkok. So let's now look at how do we route in computer networks. We choose the best path. Then the question arises, how do we define best? And we have different metrics, different ways to measure the best path. Our example will have 6 or 7 nodes in it. Real networks may have hundreds of nodes, even larger, and in which case you need automated approach for finding the best paths and also for discovering information about those paths, which we'll talk about today. A routing algorithm, think as in simple terms, a routing algorithm takes some information about the network. It takes a source and a destination node, and it returns a path between that source to that destination. So a routing algorithm finds us the best path. That's its goal. What we require of such an algorithm is that it gives us the correct path. If I want to reach node 6 and the algorithm returns me a path to reach node 4, then that's incorrect. That's not a good routing algorithm. That's an obvious requirement. So we need correctness in our algorithm. We need simplicity in our algorithm. That is, calculating the least cost paths may take time. Finding information about those least cost paths may take time. So we'd like to have an algorithm which is as simple as possible. So listing some of the general requirements for a routing algorithm. We would like a routing algorithm that is robust. What that means is if we have some errors in our network, we would like a routing algorithm to be able to deal with those errors by potentially finding a path around the errors, bypassing the errors. This is an example of to be an algorithm that's adaptive. That is, you're driving into Bangkok and you've chosen a path, but you discover that there are some problems. There's a traffic jam that looks to be ahead because the cars are slowing down. So you may adapt. You may turn left and try and bypass that intersection. So to adapt around errors or too much traffic or overload in the network is one requirement. So if we discover there's something wrong in the network, there's either packets being dropped or there's many packets being sent through a particular switch, then a good routing algorithm would try to find an alternate path, adapt. On the other hand, we don't want to change paths too frequently. So robustness says that I have a path from source to destination. If I find along that path there's some errors, then I'll choose an alternate path, another path. Stability requirement suggests that we don't want to change paths too often. Okay? Robustness suggests that we should change paths when we need, but we also want stable paths. We want to use the same path for as long as possible. Why? If we start sending our packets across different paths, then the delay for those packets may change, and maybe we even get reordering of packets at the destination. Changing delay and reordering of packets causes problems, especially for multimedia applications. So we have really two competing requirements. Change paths when we detect some problems in the network, but don't change paths too often, because changing paths, A, creates some overhead, and B, can impact upon our applications. So routing algorithms need to consider these requirements. These are just general requirements. We'll look at some specific approaches shortly. Choose the best path. Okay? My algorithm takes some information and returns a path from A to B. It should return the best path from A to B. If it chooses a suboptimal path, then that's not a good routing algorithm. So an optimal path, in our terms, will be a least cost path. If from A to B, there's a path that costs 10 units, and our algorithm chooses that path, but there's another path from A to B that costs 5 units, then it's a suboptimal route. We want an optimal routing algorithm. To choose best path, we usually need to know something about the network. Learning information about the network incurs some overhead. And that's what we're going to show through the examples and lecture notes today. That is, to learn about the network and therefore choose the best path, I usually need to send some special packets. I incur some extra processing and some communications overhead. We want to minimize that. We don't want to incur too much overhead. So minimize the overhead, that is, maximize the efficiency is a goal, but with zero overhead, we may not choose the best path. So we have conflicting requirements sometimes that to get the optimal paths, we need more overhead. If we want to reduce the overhead, we'll get suboptimal paths. We'll give some examples of that as we go through some more detailed cases. Fairness is try to be fair amongst the different nodes in the network in choosing paths. Here's an example. Here's a simple network. Node 1 wants to get to destination 7. Choose me a path. 1 to 7. 1 to 8. Okay, so our routing algorithm selects the path 1 to 8. Or an alternate path. So we've got two cases in this case. So we can go this long looking path, that is many hops, or this shorter in terms of number of hops. Let's say our routing algorithm for 1 to 7 chooses the long path. 1, 2, 3, 4, 5, 6, 7. Now for node 2 wants to reach 7. And let's say our routing algorithm, again we have two alternatives, 2, 3, 4, 5, 6, 7, or 2, 8, 7. Let's say our routing algorithm chooses 2, 8, 7. We could consider this as unfair in that node 2 gets the shorter path to reach 7, node 1 gets the longer path to reach 7. If our routing algorithm does this, sometimes we can say that that algorithm is unfair because it treated node 2 better than node 1. Fairness means treat all nodes equally. In a network or an algorithm that has perfect fairness, it treats all nodes equally. That is, all nodes get the same performance. In this simple example, it's possible that if the routing algorithm chooses these paths, then it could be unfair to node 1. That is, node 2 will get better performance because there are fewer hops in this case. So that's an example that we don't want unfair paths. That is, we want to treat all nodes equally, if possible. Sometimes it's not possible because there are trade-offs with optimal paths and efficiency, but ideally treat all nodes the same. We'll see some examples of these requirements as we go through, especially efficiency, optimality, and maybe even robustness and stability, not fairness though. Last week we introduced the terminology. We're going to use this example network where we have 6 nodes. These are switches. Okay, so this is a switched network. They have packets to send. We'll, in most cases, consider datagram packet switching, but they have packets to send. And if we want to send packets from node 1 to node 6, then we need to choose a path. The numbers next to the links indicate a general cost for using that link, where the cost is derived from some metric, some way to measure cost. And there are different metrics. we'll come back to the previous slide. Some of the common metrics are listed here. 4 example metrics. How do we assign these numbers to the links? Well, it depends upon who is building and operating the network. So it depends upon the network operator as to what cost metric they will use. So how do these numbers are derived? A simple, or one of the simplest metrics for path cost is hops. What's the least cost path from node 6 to node 1 if we use hops as a metric? Node 6 to node 1. The metric is hops. What is the least cost path? To get from node 6 to node 1, if the metric is the number of hops, what is the least cost path? What is the path, the full path? If the metric is the number of hops, I want to get from node 6 to node 1. What's a hop? Really, traversal of one link is a hop. So if the metric is the number of hops, the least cost path is 6, 3, 1. There's 1 hop, 2 hops. If the metric was number of hops. The numbers here do not indicate the number of hops. But if we change them, that now we use a different metric to measure the least cost or the cost, we say it's the number of hops, then 6, 3, 1 would be the least cost path. Alternatively, we could change all these numbers to be 1. Because if number of hops is used, the cost from 1 to 4 is 1 hop. From 6 to 5 is 1 hop. So we'll change all these numbers to 1 if the metric was the number of hops. Number of hops. That's a common metric in networks. It's very simple. All links get the cost of 1. And therefore we just find the least cost path as the least number of hops from one node to another. That's one metric. It's very simple because it only needs information about the link, like who we link to. That is, the cost is 1 in all of these numbers. But we can use more complex metrics which better reflect what a best path may be. Because an example, where are my pens? In this case again, from 1 to 7, if we use number of hops, least cost path is 187. Okay, 3 hops versus what have we got? 6 hops. If the metric is number of hops, 187. So the metric is the thing that we use to measure the cost of using a path. If it's hops, then 187 is at least 1287, sorry. But let's say we have a different metric. These links have some, the links and associated queues have some delay with them. So the delay across this link may be 2 milliseconds. And the delay to send a packet across this link may be 1, this is 3, 2, 1 and 4, all in milliseconds. And the delay across this link is 5 and this one's 10. If our metric is different, is delay, choose the path with the smallest delay. Then now we see, okay, 2 plus 1 plus 3 plus 2 plus 1 plus 4, we have 13 along this path. And 1287 has 2 plus 5 plus 10 has 17. Now the best path is 1, 2, 3, 6, 7. Okay, this path. So depending upon our metric, our best path changes. If we care about getting our packets quickly to the destination, then if we know information about the delay, then that's better to use delay. Sometimes it may be hard to know what the delay is. Okay? If we cannot measure the delay, then we may have to revert back to hops. In many cases, the more hops, the larger the delay, but not always. Okay? So we can use different metrics. Hops, delay, throughput could be another metric. Maybe these links have a capacity of 1 megabit per second. Here we can, or maybe this is 100, 1, 10, 1, 2, low capacity on this path, but here we have a higher capacity. That is, we can achieve a higher throughput along this path. So therefore choose the path that gives us the higher throughput. It's a little bit more complex of how to calculate or associate cost with throughput. We'll see that in another example. Financial cost is another thing. This is a network across the world. So the links between Bangkok and Singapore, someone has to pay money to send the data through that link. Okay? So there's some cost associated with using a particular link, a financial cost. So we can assign financial cost, choose the path that gives us the minimal financial cost. Or we could combine the factors in some weighted function. So there are different criteria for assigning general costs to the links. Once we can assign numbers to the links, like we have in this example, then we can use a least cost routing algorithm to find the best path. And one algorithm is, of course, Dijkstra's algorithm. Bellman-Ford is another popular algorithm. They are algorithms. Given this information, they will find from node 1 to every other node the least cost paths. You've studied those algorithms in some other course, I'm sure. So in the exam you can answer questions. Using Dijkstra, find the least cost path from node 1 to node 6. Okay? Good. Okay? All right, everyone remembers Dijkstra? From our perspective, I know you all know Dijkstra and those other algorithms, so we know that we can use them to calculate the least cost path. I would not ask you in the exam to use them. The examples we'll use, we should be able to just look at and find the least cost path. But in practice, we'd use some algorithm to do it for us. So, when we say the least cost path, then in fact we need to define what is the metric. How do we measure cost? And there are different metrics. Hops, delay, throughput, financial cost. There may be a metric like security, or consider political factors. You need to send your traffic from Thailand to the UK. It may be you want to avoid sending all your packets through a particular country. You don't trust that country. Or there are laws against sending data through a particular country for protection, privacy laws. So you may have a routing that avoids going through a particular location. So the metrics could be more complex than the ones that we've seen here. If we can relate the metric to a number, then we can find the least cost path, whatever the number represents. So that's what we're going to go through now is when people design routing algorithms, what are some of the criteria they consider in the design? One of them is the metric, the performance metric. That's one of them. But there are other things. When is a path selected is one example, or is one design choice. Who selects the path? Which nodes provide information about the network status, and how often that is updated. We'll spend most of today going through those, or answers to those questions. I'm going to go through firstly the decision time and the decision place, and we're going to use to demonstrate this example. So one question that we have is, when should we choose a path? When do we make a decision on which path to use? If we're using, for example, datagram packet switching, we're using datagram packet switching and we want to send some packets. We've got many packets to send from node 1 to node 6. Then for that first packet we have to send, we can choose a path. Okay? For the first packet we calculate, okay, the best path from 1 to 6 is 4, 5, 6. And we send that packet along that path that goes from 4, 5, 6. The next packet, we can make another decision. Which path to use? 4, 5, 6. While 4, 5, 6 is the least cost path, we'll keep using it. But of course the path characteristics may change. Let's just say we've sent 10 packets across the path 4, 5, 6 and all of a sudden the cost of this link from 4 to 5 jumps from 1 up to 10. And now the next packet I want to send from 1 to 6 using datagram packet switching, if I recalculate the paths, where do I send it? Another one. All right, we will not say which one, correct? But we would not send it on 4, 5, 6 because it would be larger. If this was 10, then a cheaper one is 1, 3, 6. That's 10 as well. This would be 1 plus 10 plus 2, at least 13 here. So if this cost goes up, there may be a better path. So the point is with datagram packet switching, we can decide per packet. That is, we send packets across the least cost path. If that path changes, we send the packets across the new path. And we keep sending the packets across the path which we calculate as the least cost one. So when to decide on which path to use? Every packet with datagram packet switching. As a result, some packets may go on one path, later packets may go on a different path. That's possible. With virtual circuit packet switching, remember what we do before we send our data packets, we set up a connection. So node 1 has data to send to 6. It sets up a connection and the least cost path for that connection is 1, 4, 5, 6. With virtual circuit packet switching, once we select that path, all the packets use that path. They go along the same path. So I select the path 1, 4, 5, 6. I start now sending my packets 1, 4, 5, 6. The cost of this link goes up to 10. With virtual circuit packet switching, I keep using the path while I've got the connection set up. Even if the cost goes up, I will keep using it because I've chosen that path when I set up the connection. So in this case, we'd say we choose a path per connection. Every time we set up connection, we choose a path and use that one path for the duration of the connection. In the slides, I think it says per session. Same meaning in this case. That is here. Datagram packet switching per packet. We decide per packet. Virtual circuit packet switching per session or per connection.
What do you call that?
Virtual circuit packet switching. One of our 3 types of switching from the previous topic. So there are different approaches that we can use here. We could in fact have alternatives. Instead of per packet, we could modify to say, okay, recalculate every 1 minute or every 10 packets. So it doesn't have to be every individual packet, but in the general case, every packet we could choose an alternate path. With virtual circuit packet switching, we set up a connection, use that path for the duration of the connection, and then when we set up a new connection, then we may choose a different path. As a result, where are we? Wrong way. With virtual circuit packet switching, if I chose the path 1456, that's the optimal path when I choose it. I start sending my packets along that path. All of a sudden, this cost goes up to 10. With virtual circuit packet switching, I keep using that path. It's a suboptimal path. It's not the best path in this case, but I keep using it because I use it for the duration of the connection. So there's a trade-off there of how often do you choose it. The less often you choose the path, the more chance you may get a suboptimal path. That's when to decide. Another thing, and it's on the slide with the green box, is what is it? Who decides? Who decides on the path to use? Three approaches. So what we're doing is going through different design criteria for routing algorithms. We can choose different metrics. We can have different approaches for when to decide on which path to use. We can have different approaches for which node choose. this is of no use then. That is who decides and when they decide